which of the following is a critical point of the function f of x, which is log of x to the fourth plus 1 minus 6 arctangent of x squared. And we have some choices, 1, root 2, root 3, 2, or 3. Do we have an answer? D? D or B? My hearing is not that great. C as in yes, or C as in... Okay. C. C, root 3. Okay, so critical points, we take our derivative, because we don't have any boundaries, so okay, take the derivative, and the derivative will tell us. So the derivative of log of x to the fourth plus 1, whenever you're taking a derivative of log, whatever function's on the inside goes in the denominator, the derivative of that goes in the numerator. So 4x cubed over x to the fourth plus 1. Arctangent's a little bit more complicated. It's 1 plus whatever's on the inside squared goes in the denominator, and then the derivative of what's on the inside goes in the numerator. Put it together, you get 4x cubed minus 12x over 1 plus x to the fourth. And you can factor out 4x upstairs, so that's 4x times x squared minus 3. Now we take a look at this and say, okay, is this ever undefined? Well, only thing that might worry us is division by 0, but 1 plus x to the fourth is not going to be 0, so we don't have to be worrying about undefined. And then we say, okay, does it ever equal 0? Now this is not pointing to the denominator, it's just pointing to the whole expression. And it says, well, yeah, at x equals 0, but that's not on the list. Or when x squared equals 3, which gives us two possibilities, plus or minus root 3, and root 3 is on the list. So, okay, cool. So finding critical points comes down to our derivatives. All right, any questions? Now, today we're going to be able to go one step further. See, right now we can find critical points, but today we'll get to say, and now we can say something about those critical points. So that's where we're heading for today. But first, our thought for the day. And another dubious citation. A lot of people think this goes back to Mark Twain. It's unlikely, but he could have said it. History doesn't repeat itself, but it often rhymes. And which is to say that you'll see that there are patterns. This goes back to the idea of, math is really built off of patterns. And the sooner you can start to recognize and say, oh, I've seen this before, so I know what's going to happen. I know the next steps. And you'll discover math doesn't have all that many ideas. It's often just a few simple ideas, and it's just a matter of putting them together. So, all right, now that's our thought for the day. Okay, so what's the goal for today? Well, we want to talk about the notion of increasing and decreasing. So, we'll start there. What does it mean to say we're increasing? Well, increasing means we're going up. The function is going up. And so there's this sort of formal definition, but you should just say, I'm going up. That's increasing. And what's the formal definition says, well, we're increasing on some interval if, when I look at any pair of points, if C comes before D, then f of C is less than f of D, which is just a way of saying, if you draw the picture, if here's C and here's D, that f of C has to be below f of D. So in other words, as you move from left to right, the value of the function has to move up, has to increase. Similar way, we have decreasing going down. And it's, again, there's a technical definition, but just the intuition, we're going down. So what's the technical definition say? Well, suppose you pick 2 points C and D. Then if C came before D, so there's this ordering, then I look at the values, then f of C is above f of D. So in other words, as you move from left to right in your inputs, your outputs decrease. That's decreasing. There's a phrase that you may hear of. We don't use it very much in this class, but it does show up in some places. And it says, if your functions are either always increasing or always decreasing, then we call them monotonic. Mono here means one. And tonic, it's a type of drink. So it's an idea that requires you to have one drink to understand. Wait, no, that's not what it means. That's something else. Basically, it's sort of one tone or one behavior. All right. Well, how do you know if something's increasing or decreasing? Because that seems like a very technical requirement. You have to check a lot of things. Is there a simple thing to do? And can we use the tools that we've developed to help us figure out where things are increasing and decreasing? Well, and the short answer is, of course, yes, we can use the tools we've developed, which is to say, derivatives tell us a lot of information. So recall that derivatives tell us what is happening nearby. And in particular, when we think about derivatives, we're thinking about they're giving us information about the function, and they're giving us the slope of our tangent lines. And it's easy to tell if lines are increasing or decreasing. How do I know if a line is an increasing function? What do I look for? The slope is greater than 0. Slope is positive slope. How can I tell if a line is decreasing? What am I looking for? Negative slope. And now we're like, well, we've got derivatives. It's telling us the slope. So it's telling us about increasing, decreasing locally. So where the derivative is positive, we have to look like a flat thing that's going up. So we're locally increasing. Where the derivative is negative, we locally look like a flat thing going down. Locally, we're decreasing. And then we say, aha, we can use our derivative to figure out where we're increasing or decreasing. We just say, look for the sign. We saw the sign, and it'll open up our eyes. We saw the sign. Where the derivative is positive, we can say, for sure, it's increasing. Where the derivative is negative, we can say for sure that's decreasing. And then we say, okay, but where do we change? So how can I change from being a positive to a negative? Think of your function. If I'm positive and then I'm negative, what had to happen? You what? Well, don't think about it in terms of the slope. Just think of it literally as a function. I'm positive here. I'm negative here. What had to happen? You had to either go through 0, or you had to jump. Go through 0, or something breaking down is what we call critical points. So our great aha says, hey, if I want to know increasing, decreasing, the key is find the critical points and then look what happens in between. What happens in between, I can figure out the signs. The signs tell me the behavior. And then once I have that, life is good. So, that's our basic plan. Any questions about this part so far? Okay. In that case, so the procedure. How do we find where we're increasing, decreasing? So first step, we're going to find the critical points. And when we talk about finding critical points, what does that mean? Yeah, find where the derivative is 0 or the derivative is undefined. Okay. Once we finish step 1, step 2, we draw the number line. And what happens is we're going to cut the number line up into pieces, splitting it into intervals. And we're going to use what we found in step 1 to tell us how to cut it up into pieces. Now here's the nice thing. For each piece, it's increasing or decreasing. There's no like, oh, this piece might be a little bit increasing, might be a little bit decreasing. No, no. It's either increasing or it's decreasing. Now, you might say, okay, well, how do I know which one it is? You test it. But you don't have to test everywhere. You just have to test one-where. One place. So 1 point for each interval. Because whatever the sign is at that point, it's the same sign. And increasing, decreasing is a sign result. We are not after the size of the number. We're after the sign of the number. All right, so we found our critical points. We use that to chop up our line into intervals. We're testing each interval to see the sign. Finally, where we see positive sign for the derivative, we're increasing. Negative sign means decreasing. And it is possible to combine. If I see an increasing immediately followed by an increasing, we just glue them together. So let's do an example. All right. Find the intervals for which the function t to the fifth plus 5t to the fourth minus 20t cubed minus 31 is increasing, and the intervals, it is decreasing. All right, so we have our function. Step 1, what should we do? Find what?
The critical points by taking the derivative and setting it, finding where it's 0.
Okay, so step 1, take a derivative. It's a pretty safe bet that taking the derivative is a smart strategy at this point in the class. So derivative of t to the fifth, 5t to the fourth. Derivative of 5t to the fourth, 20t cubed. Derivative of 20t cubed, 60t squared. And the derivative of 31 is 0. Is that ever undefined? No. It's polynomials. Polynomials are nice. Polynomials are lovely. Okay. So it's never undefined. Cool. Could it be 0? Well, let's try to factor it. Can we do anything to help simplify the factoring? Yeah, we can pull out a common. They all have a factor of 5. They all have at least a t squared. If you pull out 5t squared, what's left? T squared. 4t minus 12. Okay, does t squared plus 4t minus 12 factor? Sorry, what? Positive 6, t plus 6, negative 2 and t minus 2. Let's check. T squared. Okay, that's good. Minus 2t plus 6t, 4t, that's nice. And minus 12. Ah, ha, 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 ha. Yes. Nice. Okay, so we took our derivative, wrote it in a nice way. Now, if we set it equal to 0, we can say, aha, we can see the critical points. What are our critical points? So critical points, 0, negative 6, and 2. Okay, so that's step 1. Find the critical points. Step 2, draw a number line. Okay, there we go. See how easy drawing a number line is? It's like drawing a line. And then you say, this is a number line. And people are like, yep, okay. And we have 3 points, so we mark 3 points. And you don't have to be very precise about the spacing, but you do have to get them in order. So what's the right order for these points? Negative 6, 0, 2. So we're putting them in the right order. So now we've chopped it up into 4 pieces. So the next thing is to test each piece. All right. It doesn't matter which order we test. So Let's suppose we start here on the right. So how do you test? Well, the answer is you pick a number. So is there a convenient number bigger than 2? 3. Can I pick a bigger number? 100. Yeah, I could pick 100. I could also pick pi or e, anything as long as it's bigger than 2. But 3 is nice. So sort of remember, we love ourselves. And by that, pick easy numbers to work with. Don't be like, oh, I'm feeling like a square root of 7 today. No, you feel like a 3. We care about ourselves. Okay, so plug in 3. Now you can plug it in here. I often find it's easier to plug into the factored part because I pay attention to the sign. So for 3, we have positive, 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 all together, positive. So f prime positive. Okay, what's the convenient number between 0 and 2? 1. Start plugging in. We get positive, positive, negative. End result? Negative, right? A plus, plus, and a minus. How about between -6 and 0? -1 sounds pretty reasonable. The first term? Positive, because you're squaring. Here, t plus 6. Positive, t minus 2. All together, positive, positive, negative, we get negative. Okay, how about something below -6? Well, but what's the number? Let's start with the number. -10? That's fine. -7? But remember, we only care about the sign. So factoring doesn't make too big of a difference. So -7 squared, positive. -7 plus 6? Negative. -7 minus 2? Negative. Positive, negative, negative. End result? Positive. 2 wrongs make a right. Wait, no, that's not it. But 2 negatives make a positive. Okay. So, we've now, we did step 2, then we did step 3. For each interval we picked a value, we plugged it in. We can't pick these values, -6, 0, and 2, because that doesn't tell us anything. So, we're ready to write down the intervals. Where are we increasing? What are our intervals? So we look for where the derivative is positive. So here the derivative is positive, so they were increasing up to -6. So okay, so for increasing, we have x less than -6. Anywhere else where we're increasing? From 2 up. This is also increasing. So x greater than 2. Okay, how about for decreasing? What intervals are we negative? Well, certainly this interval. So -6 less than x less than 0. How about from 0 to 2? That's also decreasing. Now, can we combine these? Yes or no? I mean, it kind of tells us that you can, because it says the words can combine over there. Are we okay to combine? Yes. Yes, we are. We're okay to combine. Now, you might say, well, what's going on? Well, the answer is what's going on is that the function, I don't know exactly what it's doing, but it's coming down, levels off, and then it goes down again. So that's sort of the flavor of what the function is doing. But if you think about the definition of decreasing, no matter which points you pick, if I pick this point and this point, then I'm good. If I'm over here, if I pick 2 points to the right of 0, I'm fine. But even if I pick 1 point to the left and 1 point to the right, I'm still fine. Everywhere is fine. So you can actually glue them together. And I will say, there is mild controversy in the math department about one aspect. And I know you'd be like, what? I thought the mathematicians got along. We do okay, but there are some places where we disagree. So I should tell you, I'm in camp, I include the endpoints. So for me, it would be x less than or equal to -6, x greater than or equal to 2, and -6 less than or equal to x less than or equal to 2. And there are others who have not seen the light of Newton who wouldn't do that. But someday, perhaps if I continue to proselytize, I will bring them into the fold. Yes?
Can we write it in interval notation, or do you want us to write it like that?
You can write it in interval notation. Do you prefer interval notation? Yeah, okay. So for those who love interval notation, this one would be -infinity to -6. This one would be 2 to infinity. And here, -6 up to 2. Yeah, interval notation is fine. And the people who grade it are smart enough. They know how to handle both variations. All right, any questions on finding intervals where things are increasing or decreasing? Okay. Well, in that case, let's look at this problem where it says determine the intervals where y equals x cubed minus 3x squared minus 9x plus 17 is increasing, and where it is decreasing. Maybe a simple check. Does someone have the interval where it's decreasing, or one interval where it's decreasing? All right, I see somebody cautiously raising their hand. -1 to 3? Sounds good to me. Good. All right. So we take our derivative. We can factor out of 3. It factors. What are the odds? Really good. Our teachers like us. They want us to be able to solve problems. Okay, so we factor that out. And we say, okay, good. So now we can see what's happening. We split our number line up into 3 pieces. It's positive, then negative, then positive. So it's increasing from -infinity up to -1, or for all those people who love other notation, we'll write the other notation. And then from 3 up to infinity. And then it also is increasing in the interval from -1 up to +3. All right, good. Now this gives us some idea of how the function is behaving, but what do we do with this information? Well, we can use this to help us understand critical points. And here's the idea. The first derivative tells us how the function behaves near a critical point. And so we can use that to say, okay, given that that's the case, we can say something about what kind of critical point. Because I don't know if I've said this today, but what's important about critical points? Why are they critical? Why do we keep calling them critical? What's special about a critical point? Do you remember what makes a critical point so critical to our understanding? Well, that's where a critical point often comes from. But this goes back into like, why a critical point?
It shows like the change in behavior of like a certain function.
Well, certainly there are certainly nice changes of behavior, but there's something critical going on at critical points. Potentially critical. What? Maxes and mins. So the reason we cared about critical points is we care about max and min. And this is why people like calculus. It's because we come in and say, hey, you know how you like money? We can help you make more money. We can optimize. And people are like, we like money. Tell us more. So I shouldn't say that's people's only motivation. It turns out it's very effective. So critical points are trying to get the most out of your situation. Like we are trying to make something the most efficient, the fastest, the slowest, the largest, the smallest. We are optimizing it. And the critical points tell us where those optimums are. But if you have a critical point, you'd like to know what kind it is. Because you might say, oh, this is a critical point. You say, great. But is it where you're making the most money? Or is it where you're making the least money? That's an important distinction you'd like to know. So that comes down to what we call classifying. Okay, so the first derivative test is to say, look at your critical point. C is a critical point. And then look at the left and the right. What's the behavior to the left of your critical point? What's the behavior to the right of the critical point? And there's 4 cases. So let's think about it. So the first case here, if I am positive before C and negative after C, think your intuition. I am positive. What's happening before C? If I'm positive, my function is doing what? It's increasing. We're going up. If I'm negative after C, what's happening to our function? Decreasing. We're going down. So what kind of point do we have? We have a local max. And I'm emphasizing local because I can only say what's happening nearby. So if we're increasing before the critical point, decreasing after, we were going up then down. We're a max. All right. Well, what if we're decreasing before the critical point and then increasing after? So decreasing means we're doing what? Going down. And then we're increasing, which means we're doing what? Going up. What kind of point are we at? Local min. So the first derivative is telling us the local behavior, and then we're figuring out, oh, well that means we have something going on. Okay. Well, what if we're going up and f prime positive and f prime is again positive? What does that tell us? We're going up and then we're going up. So what is that? Yeah, good answer. Nothing. It's neither max nor min. Okay, what if we're negative and negative? What's our behavior? Going down, going down. So we're neither again. And that's the rule of thumb. Now, I will comment, we're not going to go through all the cases, but you may have a critical point which is an endpoint, in which case you only know the behavior on one side. But that's okay. Suppose we say our function stops at C, and I tell you that the derivative is positive before C. Then what kind of point would that be? It means we're going up, and then we stop. So it's a local max. When in doubt, just draw the picture. Am I going up? Or am I going down? Just a very simple picture, up or down. And then say, okay, am I max or min or neither? And then it works itself out surprisingly well. Now we've done a few problems where we've tried to classify points. Or, sorry, we've tried to do increasing, decreasing. Let's pull some stuff back here. So we had t to the 5th plus 5t to the 4th minus 20t cubed minus 31. And for this interval, we had -6, 0, 2. So you do the same thing. You find your critical points, and you test your intervals for increasing, decreasing. So I'm just copying our previous work. All right, so for this function, what can we say about -6? What kind of point is it? This is a local max. We're going up, then going down. How about 0? It's neither, because we go down and down again. How about 2? Down, then up, so it's local min. So we have one local max, one local min, and a point that's neither. Okay. Let's try the other function, which we did. So our x cubed minus 3x squared minus 9x plus 17. Well, we had our intervals -1 to 3, and we said we're positive, negative, positive. So, what kind of points do we have? What is -1? We're positive, negative, local max. When in doubt, just think of positive means going up. And just sort of say, if I'm going up and then I go down, what kind of thing goes up then down? Well, that says I kind of went over a hill. So that's a max. How about 3? What kind of point do we have? Local min. We went down then up. So this is the classification. This is the first derivative test. And you might say, oh, you called it the first derivative test. Will there be more? Yes. But that's for another day. All right. Let's start from scratch and do a problem where we find and classify the critical points of the function h of y, y plus 1 over y squared plus 8. Okay, so for finding and classifying critical points, our first step, take a derivative. What rule will we need to take this derivative? Quotient rule. Okay, so the bottom times the root of the top, so y squared plus 8 times 1, minus the top, y plus 1, times the root of the bottom, 2y, all over the bottom term squared. So, quotient rule. Okay, we should probably clean this up because we have to work with it. So, what do we do? Well, y squared plus 8 times 1 is y squared plus 8. What will this part become? Distribute the 2y through, and don't forget about the minus. Minus 2y squared and minus 2y. So we get y squared minus 2y squared is minus y squared minus 2y plus 8. Well, I prefer the coefficient of y squared to be positive, so I'll factor negative out. So y squared plus 2y subtract 8 over y squared plus 8 quantity squared. Okay, can we do anything with this expression? Sorry, what? Well, I don't know if we can do a lot with the bottom. Does anything happen with this part, y squared plus 2y minus 8? Can that be rewritten? Could it be factored? Did they give us something nice enough? Is it possible? Were they really nice this time? And if it does factor, how does it factor? I'm writing it like it does factor. What is it? Y plus 4, y minus 2. Okay, I think that's about as simple as we can hope for. All right, so critical points. Is this ever undefined? The only thing we'd worry about when we have polynomial over polynomials is if the denominator, is the denominator ever going to be 0? No. So we're okay. We're not going to be undefined. Is it ever 0? In that case, look at the numerator. Is the numerator ever 0? Okay, so where are the critical points? So when does y plus 4 equal 0? Negative 4. When does y minus 2 equal 0? Positive 2. So draw our number line. We have 2 critical points. Mark 2 points. Put them in order. Negative 4, positive 2. Okay. So the next thing is we need to test each interval. Same thing as increasing, decreasing. We're testing each interval for the sign. Doesn't matter which order you do it. Maybe we can start in the middle. Is there a convenient number between negative 4 and 2? 0 is very convenient. Okay, plug in 0. The denominator will always be positive, so focus on the numerator. Negative, positive, negative. All together, it becomes positive. So h prime is positive. Okay, do you want to do the right interval or the left interval? Left. All right. What's the number below negative 4? Negative 5. I know you're thinking like, oh, I got to pick the right number because if I don't pick the right number, it's going to give me a weird answer. No. Any number. Just pick a simple one if you can. Or if you want to be exotic and pick like negative 7, that's okay. That's great too. Okay, but negative 5. There's a negative. Negative 5 plus 4? Negative. Negative 5 minus 2? Negative. Negative, negative, negative. All together? Negative. 3 negatives make a negative. I like to think of it as like a negative is like you turn around. So if you have 2 negatives, you turn around twice, you're back pointing in the direction you started. 3 negatives, it's the same as turning around once. So it's like a single negative. Okay, number bigger than 2. 3. Okay. Negative. Okay, 3 plus 4? Positive. 3 minus 2? Positive. A negative, positive, positive. All together? Negative. So, we took our derivative. We found our critical points. We drew our line. We've tested our intervals. And now we say, what's going on? At negative 4, what's happening before? What's happening after? Before negative 4? We're negative, we go down. After? Positive, we go up. So we are a local min. At 2, before we are positive going up. After we're negative going down. So we are a local max. And There we go. So we would say -4 local min and +2 is a local max. All right. So there's a few minutes left here. Here's one. Here's another example. Here's a function, f of x equals e to the x over 4x squared plus 3. Which of the following is true? F of x has no local max or local min. F of x has a local max at x equals 0. F of x has a local min at x equals 0. F of x has a local max at x equals 3/2. Or f of x has a local min at x equals 3/2. Now, I'm not claiming you can just look at this and be like, aha, I see the answer. But you have a couple minutes. See if you can make some progress. So sometimes, even if you can't get the answer, if you can rule stuff out, that will help. So the answer is E. If you take the derivative, I made a note, the derivative at 0 is not 0, which rules out B and C. So even if you didn't do the whole problem, if you just did that, you could rule out 2 out of the 5. And it's probably not A, so you get a 50-50 shot. So, all right, that's it for today. Hope you have a great day.